Welcome back to the deep dive. We are here to take a massive stack of sources, articles, research papers, biographies, and really just distill them down into the essential knowledge you need, giving you that deep understanding without all the information overload.
And today we are profiling, well, arguably the most prodigious intellect in the history of science.
We're talking about Leonhard Euler, born in Basel in 1707. And if you had to pick just one person who completely dominated the intellectual landscape of the 18th century, it would have to be him.
Oh, absolutely. He wasn't just a mathematician, though that's what he's famous for. The sources all confirm he was a polymath in the true sense of the word. A physicist, an astronomer,
A logician, a geographer.
and a pioneering engineer. He really did it all.
And when we use a word like prolific, we are not exaggerating. I mean, his collected works are so massive, they're still not even fully published.
It's a project that's been ongoing for over a century. Right now, it's clocking in at around 80 volumes. And that scale is exactly why these later titans of mathematics spoke about him with this almost religious awe.
Right. You have that famous quote from Pierre-Simon Laplace, who basically commanded everyone, read Euler, he is the master of us all.
I mean, that's the kind of endorsement you only get from someone who recognizes pure foundational genius when they see it.
And then there's Carl Friedrich Gauss, another absolute heavyweight in the history of math. He echoed that same sentiment.
He did. He said that studying Euler's works will remain the best school for the different fields of mathematics, and nothing else can replace it.
So our mission today is to give you that best school shortcut. We want you to walk away from this understanding not just what Euler discovered, but really how he changed the way we all think about the physical world and even the language we use to describe it.
To really set the stage for his career, you have to think about this. His entire professional life was spent traveling between two of the most powerful, most demanding intellectual centers in Europe.
He served the Imperial Russian Academy of Sciences in St. Petersburg.
And the Berlin Academy in Prussia. He was essentially managing the scientific output for competing empires. It speaks volumes about how indispensable he was.
It really does. But here's the critical initial aha moment for you. I think this is the key piece of knowledge for anyone who's ever struggled through algebra or calculus.
Go on.
Euler didn't just solve these high-level abstract problems. He created the toolkit. He literally invented or popularized the symbols that are the bedrock of all modern mathematical communication.
Let's really linger on that because it's so important. When you see fx written on a blackboard, the notation for a function, that's Euler.
When you use the constant e for the base of the natural logarithm Euler's number, that's him.
If you ever encounter the imaginary unit, the square root of -1,
That's Euler.
the capital sigma for summations.
And even the standard use of the Greek letter for the circle ratio, all of it. It all owes its common, everyday use to Leonhard Euler's incredible standardization efforts.
He wasn't just a scientist. You put it perfectly earlier. He was a linguistic architect for science. He took this fractured, kind of personalized system of notation and gave it a unified, universal alphabet.
And that made communication across borders, across disciplines, not just easier, but possible.
Okay, so let's unpack the path that led to this monumental contribution. We have to start with his early life and education, the genesis of this genius.
Right. So he was born in Basel in 1707. And the first thing that really jumps out from the sources is how deep his connection to the scientific establishment was, right from birth.
It runs right through his family tree, doesn't it?
It does. His father, Paul III Euler, was a Reformed church pastor. But, and this is the key detail, he was also highly educated. He had actually studied under Jacob Bernoulli, one of the first pioneers of calculus, right there at the University of Basel. So that mathematical tradition was literally in the household from day one.
Exactly. He grew up in Riehen, near Basel, and got his initial instruction from his father. That was then supplemented with some private tutoring from a young theologian named Johannes Bernoulli. So the path was kind of set early, even though his father, like a lot of parents, had a very specific career in mind for him.
But Euler's, his innate talent just quickly outgrew that initial curriculum. He enrolled at the University of Basel in 1720 at the astonishingly young age of 13.
And this wasn't just him being precocious. This was raw intellectual firepower being applied very, very early.
And while he was there, he connected with the person who would become his most crucial mentor, Johann Bernoulli.
Jacob's younger brother, and himself one of the towering mathematical figures of the time.
And Johann Bernoulli's teaching method for Euler is the stuff of legend. It's actually something you, the listener, could adopt for your own learning, really.
Euler wrote about it himself. He detailed how Bernoulli was often just too busy for formal private lessons, but he provided something far more impactful, what he called salutary advice.
This is where it gets really interesting. Bernoulli instructed him to go read the most difficult, the densest mathematical books he could find, just digest them on his own.
And then come back every Saturday afternoon with all his difficulties and questions.
The insight here is just crucial, isn't it? Bernoulli wasn't just feeding him answers.
Not at all. By forcing Euler to wrestle with the material first, he was teaching him intellectual independence. Euler himself noted that when Bernoulli resolved one objection he brought, he said, 10 others at once disappeared.
It was a system designed to teach him how to resolve these fundamental intellectual roadblocks. It turned him into a self-learner capable of dominating, well, any field he chose.
And that guidance fundamentally changed his life path. Euler's father had strongly intended for him to become a pastor, a theologian following the family profession.
But Bernoulli, seeing the sheer depth of his mathematical talent, actively intervened. He went and convinced the older Euler to let his son pursue mathematics exclusively.
I mean, think about that endorsement. That's the 18th century's leading mathematician telling a pastor, no, your son is meant for something else entirely.
And he progressed so rapidly. By 1723, at just 16 years old, he received his Master of Philosophy.
And his thesis was remarkably ambitious. It was a comparison of the philosophical systems of René Descartes and Isaac Newton. Even as a teenager, he's synthesizing the major intellectual currents that were defining modern European thought.
But genius doesn't always guarantee a job, does it?
No. Despite his obvious talent, he couldn't immediately secure a position at Basel. He wrote his dissertation, Dissertatio Physica de Sono, a physical dissertation on sound, in 1726, but the local institution just wasn't ready to hire him.
So he looked to the wider European stage to prove himself.
And this is where we see his first real test against his contemporaries. The annual Paris Academy Prize competition in 1727.
And the problem was intensely practical. It was determining the best way to place the masts on a ship. This wasn't abstract algebra. This was applied physics and naval architecture.
And he took second place, which is a phenomenal achievement for a 20-year-old newcomer. He was beaten that year by Pierre Bouguer, who was known as the father of naval architecture.
So no shame in that loss. But that initial entry just signaled his capabilities. That minor defeat only served as motivation, really.
Oh, for sure. Over the course of his career, Euler would go on to dominate that competition. He eventually won the coveted Paris Academy Prize a staggering 12 times.
So this early period really proves the dual nature of his genius. He was capable of both the highest theoretical abstraction and at the same time solving these complex real-world engineering and physics problems. So Euler proved his worth, but Basel still wasn't the right place for him. And that brings us to Section 2, the transcontinental career that really defined his adult working life, starting with that first St. Petersburg period in 1727.
And this Russian connection, thankfully, was secured by the Bernoulli family again.
Of course.
Johann Bernoulli's sons, Daniel and Nicholas, were already established in St. Petersburg. They were the newly founded Imperial Russian Academy of Sciences. But unfortunately, Nicholas died tragically of appendicitis shortly after arriving.
Which created a perfect vacancy.
It did. And Daniel, recognizing Euler's immense talent, immediately secured the position for him. So Euler arrived in May 1727. And although he was initially placed in the medical department, he very quickly transitioned to pure mathematics.
And he lodged and worked closely with Daniel Bernoulli, right?
That's right. And he didn't just work in the academy, he completely immersed himself in the culture. He mastered Russian, adapted to the demanding schedules, and even took on an additional job as a medic in the Russian Navy.
It's worth noting, too, that he was offered a promotion to lieutenant, but he turned it down. He made it very clear that his passion was pure scholarship, not command.
But the political climate in Russia at this time was incredibly unstable. The academy had been founded under the progressive vision of Peter the Great. But after the death of Catherine I, conservative Russian nobility began to regain power under the young Peter II.
And that meant peril for the academy.
Big trouble. The conservative faction was deeply suspicious of the foreign scientists. Many of them were German or Swiss, and this led to significant funding cuts, bureaucratic hostility, and just a very uncertain future for all the academics.
The conditions became so precarious that Daniel Bernoulli eventually returned to Basel, right? He cited political censorship as a major factor.
He did. So it really took a shift in leadership to stabilize the environment. In 1730, Peter II died, and Empress Anna, who had German ties and was much more sympathetic to modern science, took the throne. And this stabilization is what allowed Euler to really flourish.
He ascended so rapidly. He was made a professor of physics in 1731, and then when Daniel Bernoulli departed in 1733, Euler, who was now just 26, succeeded him as the head of the mathematics department.
And he really cemented his life in Russia, both professionally and personally. In January 1734, he married Katharina Grissel, who was the daughter of a Swiss painter working at the Academy. This stability was absolutely vital, considering the immense intellectual output he was about to unleash.
However, despite that stability under Empress Anna, the political situation was still a long-term concern, especially after her death.
Right, and when Frederick the Great of Prussia began aggressively recruiting him for the Berlin Academy, Euler was tempted.
In 1741, he accepted Frederick's offer. There's a small detail that I think illuminates his human side. He partly justified the move by claiming he needed a milder climate for his deteriorating eyesight.
But the core motivation was the promise of a more stable, more intellectually focused environment in Prussia. The Russian Academy, by the way, was devastated to lose him.
Which really demonstrates his immense value to them.
Absolutely. They actually agreed to keep him on the payroll, paying him an annual stipend, and considering him an active member, even as he spent the next 25 years working for their direct competition.
So this transition marks the Berlin period, from 1741 to 1766, which is often cited as the peak of his sheer analytical productivity. He was in an environment perfectly tailored for scholarship.
And he wasted no time. This is where he published the seminal textbooks that formalized modern analysis. In 1748, he released Introductio in Analysis Infinitorum, an absolute foundational text on the theory of functions and infinite series.
And then, in 1755, Institutiones Calculi Differentialis, which covered differential calculus.
You have to understand, these weren't just dusty academic monographs. They were comprehensive, they were clear, and they were standardized teaching tools that rapidly circulated all across Europe. And they logged in his new notations and methods for generations of students to come.
But his influence wasn't just limited to the mathematical elite. This period also produced one of his most beloved works, and this one was aimed squarely at the lay public.
The Letters of Euler on different subjects in natural philosophy addressed to a German princess.
He wrote over 200 letters while he was tutoring Frederick the Great's niece, Princess Friedrich Charlotte, on topics ranging from philosophy and optics to magnetism and logic.
This collection is just a monument to his genius for communication. It shows this profound ability, which is rare among intellectual giants, to translate these incredibly complex scientific principles into accessible, elegant prose for a general audience.
And the letters were translated into 7 languages, published in dozens of editions, and became, really astonishingly, more widely read across Europe and the early American states than any of his specialized mathematical papers.
Yet, despite running the Berlin Academy's intellectual output and its prestige, his relationship with King Frederick II was famously strained.
The king viewed Euler as a brilliant calculator, but intellectually unrefined, sort of lacking in the courtly wit and general culture that Frederick prized so much.
And that tension was definitely heightened by the presence of Frederick's favorite philosopher, Voltaire. Euler was simple, devout, non-political. He was the exact opposite of the witty, secular, politically connected Voltaire.
And Voltaire often targeted Euler's lack of polish in intellectual debates that were outside of pure mathematics.
Right. It sounds like Euler was brilliant in a structured environment, but maybe a little uncomfortable in the cut and thrust of courtly debate.
That's precisely the dynamic the sources suggest. Frederick, who was a connoisseur of sophisticated conversation, just found Euler boring. He reportedly told D'Alembert that Euler's conversation lacked grace, saying Euler had a great genius but just could not sustain a salon conversation.
And nothing encapsulates Frederick's irritation with Euler's practical application quite like the infamous Sanssouci fountain incident. This one is always worth dwelling on.
Frederick wanted this magnificent, geometrically calculated system of water jets for his garden at Sanssouci. He tasked Euler with designing the optimal system. The result:
a spectacular failure. The water pressure was never adequate, and the fountain never worked as intended.
And the king's quote on the failure is just brutal. Vanity of vanities, vanity of geometry. He pointed the finger squarely at Euler and theoretical mathematics.
But what's fascinating here is the technical context. The sources largely agree that the king's disappointment was likely unwarranted, at least from a purely engineering perspective.
So Euler's calculations were probably correct.
Almost certainly. The calculations for the hydraulics, the geometry, the fluid movement, they were likely correct. The failure probably lay in the poor execution of the construction by the builders, or the materials used, or the practical limitations of the water source. These were issues outside of Euler's pure math domain.
So the story isn't that Euler failed, it's that Frederick preferred to blame the theoretical genius he found personally tedious rather than, say, the expensive contractors.
That sharpens the political tension perfectly. And despite all this friction, Euler's output was relentless. During this 25-year stint in Berlin, he wrote a staggering 380 works, with 275 of them published.
And on top of that, he was effectively the chief administrator for the academy.
We tend to focus only on the math, but his administrative duties were massive. He supervised the library, ran the observatory, managed the botanical garden, and, this is critical, he oversaw the publication of the maps, calendars, and almanacs, which were vital sources of income for the academy.
He was running a scientific conglomerate.
This dual role just underscores his unbelievable discipline. And we have to remember his incredible loyalty to St. Petersburg. Even while he was in Berlin, he published over 100 memoirs there. He kept contact with Russian students, and he even helped accommodate them in his own home.
That loyalty paid off during the tumultuous 7 Years' War. In 1760, advancing Russian troops sacked his farm in Charlottenburg.
But when the Russian general, Ivan Petrovich Saltykov, heard about this, he immediately paid substantial compensation for the damage.
And then Empress Elizabeth, upon hearing of the incident, added an additional 4,000 rubles, an exorbitant amount at the time.
He was an international intellectual asset. No power could afford to offend him.
By 1766, the conditions back in St. Petersburg under Catherine the Great were far more favorable. They were offering better pay and far greater recognition than Frederick was ever willing to give.
So Euler accepted the invitation to return. His demands were quite significant, reflecting his recognized worth. A 3,000 ruble annual salary, a pension for his wife, and high-ranking appointments for his sons. Catherine met every single demand.
And this marks the second St. Petersburg period, from 1766 to 1783, a time that's really defined by physical deterioration, but this unparalleled intellectual defiance.
Euler's eyesight had been failing for decades. Frederick II had already dismissively called him Cyclops due to the near-total blindness in his right eye, which was possibly aggravated by his earlier detailed cartography work.
And the famous quote from Euler when he first lost sight in that right eye is just so indicative of his character. He said, "Now I will have fewer distractions."
I mean, most people would see the end of their career. Euler saw an opportunity for deeper internal focus.
But the tragedy compounded in 1766. Complications from cataract surgery left him almost totally blind in his remaining left eye. Total darkness descended upon him. Most academics would have retired immediately.
But this is where the legend of Euler is truly forged. His productivity. It increased.
Unbelievable.
He just adapted his methodology. He hired scribes. He relied entirely on his phenomenal memory and mental arithmetic. And he dictated his work, often to his students like Anders Johann Lexel.
Let's just quantify that defiance for a minute. In 1775, years after losing his sight, he was averaging an astonishing 1 mathematical paper per week.
He was dictating analysis, formulas, and proofs entirely from memory. It is one of the most remarkable feats of sustained intellectual output in all of human history. It speaks to a mind that was just perfectly structured, able to manipulate complex, multivariable equations purely within the confines of his own skull.
And on the personal front, this period saw even more upheaval. His home was destroyed by a fire in 1771, and he lost his first wife, Katharina, in 1773.
To maintain the stability that was so crucial for his ongoing work and for his 5 surviving children, he married Katharina's half-sister, Salome Abigail Grissel, in 1776.
The story of Euler is so often told through his great discoveries, but we established earlier that his first major contribution was really the language he gave to mathematics.
Absolutely. So section 3 here is dedicated to this notational revolution, because he didn't just solve problems, he gave us the tools to write them down in the first place.
Before Euler's textbooks standardized everything, math was this Babylonian mess of competing symbols and personalized abbreviations.
That's a great way to put it. If you wanted to read Newton, you had to learn Newton's symbols. If you wanted to read Leibniz, you learned his. Euler introduced a unified logical language that every student today, whether you're in high school or graduate school, still uses.
Okay, so let's walk through the foundational symbols. First, the most elementary concept in modern math, the function.
Euler gave us fx. The use of f of x for the value of a function f applied to the argument x. Before this, expressing the relationship between variables was clunky and descriptive.
So FX gave us a concise, universally recognized shorthand.
It revolutionized algebra and calculus instantly. It allowed mathematicians to treat operations and transformations as objects in themselves.
Then we have the constants, the letter E, Euler's number, the base of the natural logarithm.
It's central to modeling continuous growth and decay, everything from population growth to radioactive half-life, and YE. The sources suggest it may have simply been the next vowel in a series of variables he was using.
But once he used it in his foundational 1748 textbook, Introductio in Analysis Infinitorum, it stuck instantly because it was clear, it was logical. It's the constant that defines exponential processes.
And crucially, he introduced the letter I for the imaginary unit, the square root of -1. This is the absolute foundation of complex analysis.
And this was a deeply abstract concept that had been debated since the 16th century.
Exactly. By giving it a simple, standardized symbol, I, Euler normalized and formalized its use. You simply cannot do modern physics, electrical engineering, signal processing, quantum mechanics without the symbol I and the complex number system it anchors.
He also helped secure the use of Britain.
That's right. While he credited the Welsh mathematician William Jones with the original use back in 1706, it was Euler's extensive use of the Greek letter in his major, widely read text that cemented it as the universal standard for the ratio of a circle's circumference to its diameter.
And it wasn't just letters, it was operational symbols too.
Right. He introduced the Greek letter dra, capital sigma, for summations. This provided a concise way to represent long or infinite series. Before dret, representing a series was just cumbersome prose. Afterwards became a clean, universally readable equation.
And the Greek letter A, capital delta, for finite differences, which is essential for numerical methods and early calculus work.
Even geometry was standardized by him. When you look at a textbook today, you see triangle sides labeled with lowercase letters, and the angles opposite them labeled with corresponding capital letters.
That clear, simple convention, that's Euler. He was ensuring that geometry problems could be read consistently across continents.
So the takeaway here is that standardization was Euler's first great intellectual act. It made math accessible and cumulative. It's so rare for one person to have such a profound and lasting impact on the global language of an entire field.
So when you are struggling through a complex physics problem today, just remember you are using the precise, organized language Euler invented, saving centuries of confusion. That's his gift to every modern student.
And now we transition from the language builder to the discoverer. Sections 4 and 5 are going to cover the sheer breadth of his original theoretical and applied research. Let's start with analytical contributions, the area where he was truly sovereign.
Right. The 18th century was dominated by the development of infinitesimal calculus, and Euler was the most powerful engine in that development. He was famous for his frequent use and development of power series.
Power series expressing functions as infinite sums of powers of x. He used them like no one before him. If you can express a function as an infinite polynomial, you can manipulate it, integrate it, and differentiate it with comparative ease.
He showed, for example, the exponential function e to the x as that infinite series. E to the x equals the sum from n equals 0 to infinity of x to the n over n factorial.
His willingness to just work with infinite processes allowed him to achieve results that baffled his contemporaries.
And the most famous example of this analytical power has to be his solution to the Basel problem. This problem had stood open since 1644, posed by Pietro Mingoli, and it had frustrated the brightest minds of the age, including the elder Bernoullis.
The challenge was to find the exact sum of the reciprocals of the squares of every natural number, so 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared, and so on.
It looked like a pure number theory problem, and they knew the sum converged to some number around 1.64, but finding the exact value proved impossible.
Until Euler. In 1735, he provided the stunning and utterly unexpected solution. The sum is exactly squared over 6.
What made this so groundbreaking was the connection. Why should a series involving integers have a result tied to the geometric constant of the circle?
It was a beautiful, inexplicable piece of unity, and it relied on a brilliant, though initially non-rigorous method where he treated the infinite series like it was a finite polynomial. He later provided a more elaborate proof, but the result stood. It was a connection between two seemingly disparate worlds of math.
And his work didn't stop with real numbers. He successfully defined logarithms for negative and complex numbers, which vastly expanded the practical reach of the logarithm function.
But the absolute pinnacle of his achievement in complex analysis is Euler's formula.
This is truly a high point. He extended the exponential function to complex numbers, linking it directly to the trigonometric functions. The formula states that e to the I equals cos plus e sin.
This formula provides the fundamental link between circular motion, so trigonometry, and exponential growth.
And if that wasn't beautiful enough, if you set the angle to quite high, you get the simplest and most elegant version, which is known as Euler's identity. E to the I plus 1 equals 0.
This one short equation is often called the greatest formula in mathematics. Richard Feynman famously called it that. And think about what it connects. You have E, the base of continuous growth, I, the imaginary unit, the geometric constant, 1, the multiplicative identity, and 0, the additive identity.
5 fundamental constants woven into one perfect expression. It just epitomizes Euler's unifying vision for mathematics.
And moving beyond those headline results, he also essentially invented the calculus of variations.
Okay, so what is that and why does it matter?
Well, the standard calculus you learned in school deals with finding the point, a number, where a function is maximized or minimized. The calculus of variations is much deeper. It finds the function, the actual shape or the path, that maximizes or minimizes an integral.
So instead of finding the quickest single speed, you're finding the most efficient path overall.
Exactly. It's essential for finding things like the shortest distance between 2 points on a curved surface, the shape of a soap film stretched between 2 wires, or the optimal trajectory of a satellite. He formulated the Euler-Lagrange equation, which is the foundational tool for this entire field.
And it's still used in everything from general relativity to classical mechanics.
He also contributed to the theory of higher transcendental functions by introducing the gamma function. That sounds a bit intimidating. What purpose does it serve?
The gamma function, which is denoted AZ, is essentially a way to extend the concept of the factorial, which is normally only defined for positive integers, like 5, to include non-integers, complex numbers, and fractions.
So it allows you to calculate something like half factorial.
Conceptually, yes. And this seemingly abstract extension proved absolutely crucial for advanced mathematics, especially in areas like probability distributions, partial differential equations, and complex analysis in physics. It generalized a key tool. And we should also mention the Euler-Maclaurin formula, another key tool he developed for approximating integrals using summation, vital for numerical methods.
Now let's pivot to number theory, because this is where Euler truly created a whole new discipline. Analytic number theory.
This was the revolutionary act of uniting number theory, which deals with discrete integers and primes with continuous analysis. He was using tools like infinite series and calculus to solve problems about numbers.
He demonstrated the power of this new approach by proving the infinitude of prime numbers. Now we know Euclid proved this using pure number theory, by contradiction. How did Euler use analysis?
He connected the divergence of the harmonic series, so 1 plus a half plus a third plus a fourth and so on, to prime numbers. He showed that the sum of the reciprocals of the primes, 1 half plus 1/3 plus 1/5 plus 1/7, also diverges, meaning it approaches infinity.
And this could only happen if there were an infinite number of terms, an infinite number of primes in the series.
It's a subtle but brilliant argument. It shows that analytic methods could yield new insight into these ancient integer problems.
And that connection led to his discovery of the profound Euler product formula, which linked the sum of reciprocals of integer powers, which later became the Riemann zeta function, to a product over prime numbers. The implications of this formula are still a cornerstone of mathematical research today.
And in pure number theory, Euler was the intellectual heir to Pierre de Fermat. He dedicated significant effort to validating Fermat's findings, but he also wasn't afraid to overturn them.
That's right. Fermat had conjectured that all Fermat numbers, those of the form 2 to the n plus 1, were prime. Euler, through brilliant calculation, proved that for n equals 5, the resulting number, which is over 4 billion, was composite, not prime.
He showed it was divisible by 641, disproving Fermat's conjecture entirely.
And he also gave us one of the most important tools in modern cryptography, the totient function. What exactly does the totient function do?
The totient function, sometimes called Euler's phi function, it counts how many positive integers less than or equal to n are coprime to n.
And two numbers are coprime if they share no common factors other than 1.
And why is that useful?
Well, it helps us understand the structure of remainders in modular arithmetic, the math of clocks and cyclical systems. Euler then used this function to generalize Fermat's little theorem, resulting in Euler's theorem.
And this theorem is critical because the principles it establishes dealing with exponents and remainders are the exact foundational base we use for modern security and encryption algorithms like RSA.
He also contributed to the classical study of perfect numbers, those numbers that equal the sum of their proper divisors, like 6, where 1 plus 2 plus 3 equals 6.
This was a fascination since Euclid.
It was, and Euler solved a long-standing mystery by proving the one-to-one correspondence between even perfect numbers and Mersenne primes. This result is known as the Euclid-Euler theorem, a perfect example of his ability to synthesize ancient geometry with modern number theory.
Okay, moving on to section 5. If Euler's work and analysis proved his theoretical mastery, his contributions to geometry, physics, and engineering really demonstrate his role as the ultimate applied genius. He wasn't just working with abstractions, he was shaping the physical world.
And the best way to introduce this shift in perspective is through the story that literally founded an entirely new branch of mathematics, the Seven Bridges of Königsberg problem from 1735.
Retell that problem for us because it sounds like a simple riddle, but it completely changed math forever.
The city of Königsberg, which is now Kaliningrad, was built on the Pregel River, and it contained 2 large islands connected to each other and the mainland by 7 bridges. And the citizens wondered if it was possible to take a walk and cross each of the 7 bridges exactly once.
Euler proved it was impossible, but the true genius wasn't the no answer, it was the methodology he used to reach it.
Exactly. Euler realized that the solution had nothing to do with the physical distances, or the size of the islands, or the length of the bridges. All that mattered was the connectivity.
He replaced the land masses with points vertices, and the bridges with lines or edges.
Right, and he determined that for a path to exist that crosses every bridge exactly once, an Eulerian path, the graph could have at most 2 vertices with an odd number of edges connected to them.
And since Königsberg have 4 land masses with an odd number of bridges connecting them, such a path was impossible.
This approach, focusing only on structural relationships and ignoring measurement, is recognized as the first theorem of graph theory. It's a complete shift in mathematical perspective, moving math from continuous measurement to discrete connectivity, a shift that is crucial for modern computer science and networking.
He made a similar profound contribution to topology, which is the study of spatial properties that remain the same even when an object is stretched or deformed.
That was through the Euler characteristic formula. For any convex polyhedron, a 3D shape like a cube or a pyramid, the number of vertices, V minus the number of edges, E plus the number of faces, F always equals 2.
VE plus F equals 2. It's just beautiful in its simplicity. So why is that the origin of topology?
Because it's a property inherent to the structure of the shape, not its size or its curvature. You can distort a cube into any shape you want. But as long as you don't break or merge edges, the count VE plus F will always be 2.
The study of this formula and its generalization to other objects is recognized as the starting point for modern algebraic topology, a field that seeks structural invariance in space.
And turning to physics and engineering, Euler didn't just apply Newton's laws. He refined them to make them more useful for the coming industrial age. In his 2-volume work, Mechanica, he reformulated classical mechanics, providing new analytic laws to better describe the motion of rigid bodies, which are far more complex than the idealized point masses Newton often considered.
And in structural engineering, he gave us 2 formulas that are absolute cornerstones for anyone building things today. First, the Euler-Bernoulli beam equation.
That equation is foundational for designing any structure that's subject to bending, whether it's a bridge, a building frame, or an aircraft wing. It describes the relationship between the beam's deflection and the loads applied to it, allowing engineers to calculate stress with precision.
And second, and perhaps even more famous in engineering, is Euler's critical load formula.
This formula calculates the exact compressive load at which a long, slender column will buckle and fail. Before Euler, structural collapse due to buckling was often unpredictable. His formula gave engineers the definitive boundary, the critical load, telling them precisely when the geometry of a column will cause catastrophic failure under compression.
It saved countless lives and billions of dollars in future construction.
His work in fluid dynamics is equally foundational, even if it's often less visible. In 1757, he formulated the Euler equations for inviscid flow.
Inviscid flow being the motion of an idealized fluid with no viscosity, no internal friction.
Right. Which, while theoretical, provides the simplest, most powerful starting point for understanding how water and air move. These equations are still the first tools used in computational fluid dynamics.
And here's a fact that just shows his predictive genius. In 1754, based purely on mathematical modeling, Euler was the first person to predict the phenomenon of cavitation.
Cavitation is the formation of vapor bubbles in a rapidly flowing liquid when the pressure drops below the fluid's vapor pressure. It's what causes noise and damage in pumps, propellers, and giant turbines.
And Euler mathematically predicted this phenomenon, these very tiny bubbles that challenged giant engineering systems, long before it was physically observed in the late 19th century.
That is true scientific prophecy.
He even weighed in on one of the great historical scientific debates in optics, disagreeing with Isaac Newton's prevailing theory that light was made of particles, or corpuscles.
Euler was an advocate for Christian Huygens' wave theory of light. His papers in the 1740s provided strong mathematical arguments in favor of light propagating as a wave. And while science eventually reconciled these two views with quantum theory, Euler's work was crucial in pushing the wave theory to dominance for a long period, ensuring the scientific debate remained dynamic and productive.
And beyond physics, his influence extended into visualization and logic. In 1768, he introduced the Euler diagrams to illustrate syllogistic reasoning.
These are the closed curves we still use today to visually represent set relationships, whether they intersect, or subsets of each other, or are entirely disjoint. While modern Venn diagrams are a refinement, Euler diagrams are the visual starting point for thinking about logical relationships and set theory.
And in the nascent field of demography, he essentially launched modern population modeling 150 years too early.
He did, in the 1760 paper, A General Investigation into the Mortality and Multiplication of the Human Species. He created a comprehensive mathematical model. He showed that a population subject to constant rates of mortality and fertility would eventually grow geometrically, establishing a fixed age structure.
And that model, the stable population model, is fundamental to how demographers study population dynamics today. But it wasn't rediscovered and widely formalized until Alfred J. Lockton did so in the 20th century.
He was 150 years ahead of the curve, defining the start of formal demographic modeling.
Finally, we get to one of his most unusual and personal interests, music theory. In 1739, he wrote Tentamine Novae Theoriae Musicae, which was an attempt at a new theory of music, trying to ground aesthetic concepts entirely in mathematics.
And this work was notoriously difficult. It was described as too mathematical for musicians and too musical for mathematicians.
It was a beautiful failure, but a failure of communication, not insight. Euler was trying to quantify harmony. He mathematically derived the gradus suavitatis, or degree of agreeableness, for musical intervals and chords.
He based this sweetness on the arithmetic of small prime factors found in musical ratios, specifically 3 and 5. For instance, a perfect fifth, with a ratio of 3 to 2, is harmonically simpler than a diminished fifth. His belief was that aesthetic pleasure was rooted in the quantitative simplicity of ratios.
He even devised a graph, the speculum musicum, to classify musical genres based on their complexity, which has recently drawn renewed interest in advanced music theory.
It just shows his relentless quest to unify knowledge. If mathematics governs the stars, mechanics, and light, well, why not beauty itself?
As we synthesize the life of Leonhard Euler, we have to just pause and consider the sheer magnitude of the mind that produced all of this. The volume of his output, especially while blind, suggests an organizational and computational ability unlike almost anyone else in history.
The famous tales about his memory are just awe-inspiring. By all accounts, he possessed a computational memory that was staggering. Nicholas Fuss, who was one of Euler's disciples, chronicled these abilities.
He had memorized Virgil's massive epic poem, the Aeneid, in its entirety. And in his later years, totally blind, he could reportedly recite the poem and instantly state the first and last sentence on any given page of the exact edition he had learned from decades prior.
And his mathematical memory was equally flawless. He could instantly recall the first 100 prime numbers and their powers up to the 6th degree, and he used those facts as computational scaffolding inside his head. This ability to run complex equations solely in his memory is why the loss of his sight barely slowed him down.
And his general knowledge wasn't just limited to math and the classics. He had comprehensive knowledge of history, Roman writers, medicine, botany, chemistry, far more than a specialist would be expected to hold.
This extraordinary mental catalog allowed him to synthesize fields and draw connections where others saw only separation. It's what makes him a truly universal genius.
The scale of his legacy sometimes needs a human touch, which brings us to a famous, persistent, but ultimately false anecdote involving the French philosopher Denis Diderot.
Right, this legend supposedly takes place during Euler's second tenure in St. Petersburg under Catherine the Great. Diderot, who was known for his atheistic leanings, was influencing the Russian court, and the empress allegedly asked Euler to publicly silence him.
The story goes that Euler approached Diderot and with perfect conviction announced a mathematical proof of God's existence. He states the non sequitur. Sir, a plus b to the n divided by n equals x, hence God exists, reply.
And Diderot, allegedly knowing nothing of mathematics, was left speechless, mocked by the court, and soon asked to leave Russia.
It's a wonderfully dramatic, if perhaps a bit anti-intellectual story. But as historians confirm, it's a legend popularized later, and it simply isn't true.
Not at all. Diderot was a capable mathematician himself, and the incident as described never occurred. The story is perhaps best appreciated as a cautionary tale about the intimidation factor of using specialized jargon rather than a factual account of Euler's rhetorical style.
His real rhetorical power was in the elegance of his written proofs, not in courtly verbal trickery.
His career came to an abrupt yet strangely fitting end. On September 18, 1783, Euler was in St. Petersburg discussing the newly discovered planet Uranus and calculating its orbit with his student Anders Johann Lexell. He suffered a brain hemorrhage and died instantly.
The famous eulogy, written by the French mathematician and philosopher Marquis de Condorcet, provides the perfect epitaph for this immense intellectual engine. He wrote, "Il cessa de calculer de vivre."
He ceased to calculate and to live.
His legacy is undisputed. John von Neumann called him the greatest virtuoso of the period.
And Henri Poincaré went even further, simply calling him the god of mathematics.
And for those who want to grasp the sheer scope one final time, the publishing effort to collate his opera omnia, his complete works, is still ongoing. The current total is 80 volumes, cataloged systematically by the Inniström Index from E1 to E866, covering every aspect of analysis, mechanics, physics, and correspondence. This body of work is the best school Gauss spoke of.
He appears on the Swiss 10-franc banknote and numerous stamps. His influence isn't just academic, it's embedded in the foundational symbols we all use to describe the universe.
So what does this all mean for you? Euler's life shows the triumph of disciplined intellect, overcoming political instability and even total physical blindness through the power of a perfectly structured mind. But let's connect back to that unusual passion we discussed earlier, his attempt to quantify harmony, the Grodus Suavitatis.
He believed musical sweetness could be derived precisely from the arithmetic of small prime numbers, the simplicity of the ratios 3 and 5. It was a mathematical definition of aesthetic beauty.
So here is the final provocative thought for you to mull over. If aesthetic concepts as subjective as musical harmony can be precisely derived from elegant, underlying quantitative laws, if beauty has a numerical root, then consider whether all forms of aesthetic pleasure or natural beauty, whether it's the structure of a flower, the flow of a river, or the shape of a seashell, might also be rooted in similarly elegant universal quantitative laws that are just waiting to be discovered.
Euler's work suggests that knowledge is ultimately not a collection of separate subjects, but one unified field where physics, art, and numbers are all connected, a fitting challenge from the master of us all.
Thank you for joining us on this deep dive into Leonhard Euler. We'll see you next time.